Well, good morning. It's a tremendous pleasure and an honor to have the chance to speak with you today. I want to thank the Swedish Academy, and I want to thank the Crafoord family, and I want to thank Professor Manabe for being my co-laureate, because I can still remember meeting him when I was a young scientist about 30 years ago, and I would never imagine I could be standing here today together with Professor Manabe. So if you're a young scientist, you should try to meet him during the break, because you never know what might happen to you 30 years later. What I'm going to try to do in this half hour is to talk about the history of ozone science, a little bit of atmospheric physics and chemistry, and tell you how my own work fit into that. I'm going to touch on the issue of whether the agreement on ozone depletion to stop ozone depletion, called the Montreal Protocol, is working. And I won't have time to go into all the details of that, but I will touch on that recent paper that received some news press coverage this past week, saying that there's what you might call a fugitive, an unexpected emission going on. And I'll talk about the issue of how the ozone hole affects the surface climate, at least in Antarctica, if not elsewhere in the southern hemisphere. So, to step back a little bit in the history of this problem, the initial interest in ozone depletion really began in the late 70s, actually mid-70s to early 1980s, when it was predicted that if we kept using chlorofluorocarbons and the halons, which are in fire extinguishers, and they contain bromine, which is even more damaging towards ozone, that we might expect to deplete the ozone layer. And we thought we would see a 5 to 10% change in 100 years. So it was a relatively small effect, it was far in the future. Some people said maybe they didn't believe it. It sounded like another climate change, another environmental change problem that we just heard about. But I want to just emphasize that the thing that was the primary use of chlorofluorocarbon at that time was actually something that some of you may remember, and that was the use of them for literally hairspray, deodorant, paint, oven cleaner, anything that came out of a can. The propellants that drove the material out the can were chlorofluorocarbons. And I'll get back to that in a few minutes. So in 1974, people at the University of California, Irvine, Professor Rowland and Professor Molina, wrote a scientific paper saying, hey, you know, if we keep using these things, they might deplete the ozone layer. So they were the first ones to really call the world's attention to this problem, and that's the basis for those predictions of 5 to 10% in 100 years. And they pointed out that these molecules have very long lifetimes in our atmosphere. We're spraying them all over the place, and they live in the atmosphere for some 50 to 150 years, they said. And when they get to the stratosphere, which is the only place that they can be broken down, they produce chlorine atoms, which go on to react with ozone to make this guy, chlorine monoxide. That guy comes down here, reacts with atomic oxygen, and makes the chlorine atom back again. So that guy can go right back up there and do it again and again and again, over and over. It's a catalytic cycle. You only need a little bit of chlorine to deplete a lot of ozone. And that was the basis of what I'm going to call the gas phase theory of ozone loss. And these two gentlemen shared the Nobel Prize in 1995 in chemistry, together with Paul Crutzen, who was actually my PhD thesis advisor. They were only talking about gas phase molecules, and I just want to point out that also for the students, if you read your papers, you should check them and proofread them very carefully, because you wouldn't want to win the Nobel Prize 20 years later for something that had a typo in the title, but that's what happened. But emphasizing these are gas phase molecules, small effect, far in the future. Then suddenly something really amazing happens. I was very lucky to be a young scientist at the time when the British Antarctic Survey announced the discovery of the ozone hole. They said, hey, ozone is changing in an incredible way in 1985. We're seeing 50% loss of ozone in the springtime, and in a place where no one ever said we would have any special sensitivity, namely the Antarctic. So much bigger than we thought, and much sooner than we thought, a real ozone surprise. You're all familiar with the wonderful satellite images that NASA produces every year, showing you the Antarctic ozone hole. It's a tremendous graphic image. But the British data was very important because it went back to the 1950s. You can see the ozone go up and down a little bit for the first 20 years, and then boom, it just kind of falls off the map, and that's why they wrote their pioneering paper. That was quickly confirmed by the Japanese station, the American station, and basically it gives you a graphic image. You don't have to be a statistician to see that there's been a huge change here. These are October monthly average values at each of those stations. Antarctica attracts people. People got interested in this. And so it was a perceptible problem. That's the first of 3 Ps that I'm going to argue are very important in helping people address environmental issues. When an issue is perceptible, we do a particularly good job. So why do we care about this layer of ozone in our stratosphere? Well, you know that ultraviolet light is bad for you. It can give you sunburn, which is unpleasant. But worse than that, if it happens too often, it can give you skin cancer, which is obviously very, very serious. And it can also cause cataracts and eye damage. So those are the sorts of effects that happen to humans. So I'm talking really about ozone in the stratosphere. Ozone at ground level doesn't do those things. People talk about ozone smog. That's a completely separate problem that I'm not going to talk about today. So it's good to have the ozone up in the stratosphere where it can protect us from ultraviolet light. It's bad to have it down here because it's actually gives kids asthma, and it's a real problem in that sense. But the other thing that I think is evident from looking at this is that to people, this is a very personal problem. That's the second of my 3 Ps. It's perceptible and it's personal. We'll get to the 3rd P in a minute. So where I was, at the time, I began thinking about the sorts of chemistry that might explain this special springtime Antarctic sensitivity to this chlorine. And together, particularly with my colleague Rolando Garcia, we wrote a paper that appeared in Nature in 1986, arguing that what could happen is that hydrochloric acid and chlorine nitrate, which don't react with each other in the gas phase, could react on the surfaces of polar stratospheric clouds. You may have seen these occasionally in Sweden. You can see them in the wintertime. They're incredibly beautiful. You'll see them at twilight. They look like little rainbows almost in the sky. And so they change the chemistry in a simple and fundamental way. Now you're talking about surfaces, not just gases. And it's going to be the most effective when it's cold enough to form clouds in the very dry stratosphere. We don't get clouds in the stratosphere over, say, the United States. We get them sometimes in the Arctic, but not as often because the Arctic is warmer. So I'll get back to that in a few minutes, too. So the key ingredients are, we load up the atmosphere with man-made chlorine. The amount of natural chlorine is only about 1/5 of the total that we have today. We've totally overwhelmed it with these industrial chemicals. I talked about the use in spray cans, and I'll talk about some other uses in a few minutes. We have to have extreme cold temperatures so we can get these polar stratospheric clouds, and we need sunlight to drive the photochemistry. And where the sun comes in, so there's another picture of those beautiful clouds. Hydrochloric acid and chlorine nitrate don't react with ozone. They're reservoir species, we like to call them. They're stable species. Until they get together on the surfaces of those clouds, they make this guy, molecular chlorine, which is quite unstable. It just needs a little bit of light to break down. Now you got 2 of these chlorine atoms, and they can go on to deplete ozone catalytically, and I'm not going to show you the details of that chemistry. But the key thing is that the polar stratospheric clouds are what activates the chlorine in a very special way in the Antarctic. So what does that do? Well, that gas phase chemistry that was talked about initially has some potential to affect the ozone layer, as we know. This is what a typical ozone layer looks like. So you don't have much ozone in the troposphere. You have a lot of it in the stratosphere. As you go up, you have even less. So the gas phase chemistry destroys ozone up here. It can't give you a big change in the total integrated amount between you and the sun because it can only attack the high altitudes, which is not where most of the ozone actually is. By having the polar stratospheric clouds there, you can actually hit the heart of the layer. You can take a normal ozone layer that looks like this and turn it into something that I've drawn in a cartoon form like that. So you've got to have cold temperatures, you've got to have sunlight, and you've got to have man-made chlorine. Well, the other great good fortune that I had was to be the leader of the National Ozone Expedition in 1986. So there I am on the tarmac, getting ready to get on a military airplane to go to the Antarctic to make some measurements, which I'll show you in just a moment. And 9 hours later, there we are arriving in Antarctica. It's about noontime. It's about -40 Fahrenheit, which is the same, -40 Celsius. That's the one temperature at which they actually are the same. So it's a good number to know. I thought it was the most beautiful place that I had ever seen. As you can see, even though it's noon, it's not very bright yet because it's August. So August is like February. You know how dark February is here in Sweden. It's quite dark, even darker, because I'm at a higher latitude than you down there. One of the things that we did on the National Ozone Expedition, Dave Hoffman and his colleagues launched ozone balloons, and they had an electrochemical instrument on the end of that payload, and the balloon would rise up into the stratosphere, and as it went, we could measure that ozone layer. So here's an example of what an ozone layer typically looks like in, say, August. This is actually from South Pole, but we had similar data from McMurdo in '86. You can see that by mid-September, when now sunlight has returned, like mid-March here, you begin to see a very amazing sort of bites being taken out of the ozone layer. By the time you get to the end of September, even more, and nowadays, by the time you get to early October, basically, it's all gone. So you've completely wiped it out at the altitudes, exactly the same heights that we expect it to be, because we know that's where the polar stratospheric clouds reside. So we have these wonderful signatures that tell us that this chemistry is right. I mean, it's got the right seasonal behavior, it's got the right altitudinal behavior, the loss is occurring right where the clouds reside, and we have ways that we can measure the chlorine. That was probably the most important thing that my own group did, and that's my colleague Ryan Sanders, who was very instrumental in this work. What we did was to look for spectral fingerprints of chlorine dioxide, a key chlorine molecule closely related to chlorine monoxide. We used moonlight and sunlight at McMurdo Station. And we had to sometimes get up on the roof, as Ryan is doing here, to adjust mirrors, and it was windy, it was cold, and it was an incredible experience for any young scientist. So we would take that moonlight and direct it down into our spectrograph, and we did something very much like a prism. So the white light from the moon comes in, goes through the prism and turns into different colors of light, and we can measure the absorption of that moonlight at particular wavelengths, particular colors of light. So this is what chlorine dioxide looks like. The dotted line is a laboratory spectrum, and the solid line is what we were able to see in Antarctica. So clearly, there was a significant amount of it, 100 times more than there should have been, and 100 times more than you see anyplace else. So it was I think it's fair to say it was the first marker showing us that the chlorine in Antarctica really was totally out of whack compared to other latitudes. Another very important activity were the Airborne Missions in 1987, a year later, by NASA, NOAA, and NSF, and that included an independent method to measure chlorine monoxide by a laser technique on board that plane by Anderson and colleagues from Harvard. So I wish I had time to show you all of those wonderful chemical measurements. The only thing I'm going to say is that because we had so many independent types of data, they all showed that this chlorine chemistry was extremely perturbed. We also had measurements of hydrochloric acid. We could see that the hydrochloric acid had been just destroyed. So this grew at the expense of that. We also measured the nitrogen compounds, and they all told the same story, that this chemistry was what was depleting the ozone layer, and that's me again. By now, the sun has come back, obviously, and in fact, it's not setting anymore. I think that was late October. So if we compare quickly the Arctic and the Antarctic, I've already shown you pictures that look like this, but now this is comparing historical data from the South Pole, 60s and 70s. October averages used to have a normal ozone layer, and now look what's happened to it in the most extreme cases and in the average. If you compare that to the most extreme sorts of cases that we see here in the northern hemisphere in the Arctic, definitely it looks somewhat similar. You know, we're seeing some of the same phenomena happening in March in the Arctic that we see in October in the Antarctic. We're definitely seeing bite outs, but it doesn't take it down to 0 the way it does in the Antarctic. So that's simply because the Arctic is warmer. We have significant ozone loss here, and I know that people are justifiably concerned when the Arctic ozone losses roll over Sweden, which they will do from time to time, but it's not as much as what we see in the Antarctic. I just want to emphasize that I've said a lot about American research in the Antarctic. I think it's clear that the Europeans have been the leaders in understanding Arctic ozone. I don't have time to talk about that in detail, but this is just a picture of the station in Kiruna, and a picture of a balloon launch there, and several campaigns to understand Arctic ozone losses and really figure out why there's so much less ozone loss in the Arctic have been conducted by European scientists involving many people from different countries. So, concern about this led the nations of the world to agree to the Montreal Protocol. First, they said, well, we'll just freeze these emissions. We'll not let you make any more than you made the previous year. And that was not that difficult to do in the sense that there were only ever about 20 different companies that were making the stuff worldwide, and they freeze the production, I should say. An important point. Emission is not the same as production, and I'll touch on that in a second. So let's just not make more next year than we made this year, and if you kept doing that forever, chlorofluorocarbons would have still increased dramatically because of the very long residence times, the long lifetimes of these gases. But that's not where it stopped. Once the Antarctic ozone hole was understood and accepted by the scientific community, which took a few years, the diplomats met again in London in 1990 and agreed to phase them out entirely in developed countries. And then they met over and over again till Beijing in 1999, when they agreed to phase them out in developing countries as well. So we're following very close to the 0 emission line now. And that has had an enormous effect. Let me show you just a little bit more about how it all happened. It wasn't just the diplomats at all. So if you take a look at something else now, these are the metric tons of chlorofluorocarbon sold, total chlorofluorocarbon, as a function of year. In the United States, the rest of the world, and then the total, you see something very interesting, which is sometime around 1974 or so, the American sales start dropping. The rest of the world kind of flattens, but never actually drops. That dropping wasn't due to the Montreal Protocol. That wasn't signed until 1987. It wasn't due to the discovery of the ozone hole, which didn't happen until 1985. It happened because that theory paper that won the Nobel Prize was published by Molina and Rowland. And what that did was to make people concerned. Even though it was only a theory and far in the future, many people turned away from their spray cans. So, all they had to do was that, which is not that hard. So lots of people can do things that involve environmental change when it doesn't inconvenience them too much, because people do care, actually. And if there are simple things that people can do, they will find them. That made good business into bad business for the US chemical companies, and as a result, they were pretty eager to get out of the business. In most of Europe, that didn't happen. I'll name an exception in a minute. And that's why, in fact, in Europe, people continued to use chlorofluorocarbons in spray cans well into the late 1980s and early 90s, so much later. So really, I would have to say that consumer pressure in a case like this was very important. And I really feel uplifted when I think about the role that people played in this. And since I'm here, I can't help but mention that actually Sweden was the first country in the world to announce that they were going to ban spray cans entirely. And you did that about 10 months before we did, actually, in the US. So you were the leaders of the entire world in banning spray cans, but the rest of Europe actually didn't follow suit. A few countries did. Norway did, but not everyone. So spray cans are not the only use, and I should emphasize that it's okay to use spray cans now. They don't contain chlorofluorocarbon anymore. Other things get the material out the nozzle now. But they were used in other things that were also phased out, thing after thing after thing. Styrofoam was another major use of chlorofluorocarbons. It made the little bubbles in the foam. But nowadays, you get your Big Mac in a cardboard box instead of a styrofoam box, and that's why. They were also used as solvents, and nowadays, in many of those applications, you can even use lemon juice. So it's really been amazing. What did this do for the world? Well, it avoided the whole world looking like this by 2060. So basically, the whole world would have been under an ozone hole by 2060. You would have had many, many millions more skin cancer cases worldwide. We really did save the planet. One of the issues is the replacement in refrigeration is something like this molecule, which is an HFC. It has fluorine and hydrogen, but no chlorine. So it doesn't deplete the ozone layer. Fluorine does not deplete the ozone layer. Chlorine and bromine do. But it is a greenhouse gas, and it's important for climate change. So it is also now being phased out under the Montreal Protocol. The Montreal Protocol did not have protection of climate as its primary goal. It's to protect the ozone layer. And yet, it actually did more to protect climate than, say, the Kyoto Protocol. Actually, about 5 to 10 times more, depending on how you count it. And it's about to do more again by phasing out the HFCs, assuming that that continues to move forward. That will actually shave about somewhere between 0.2 and 0.4 degrees Celsius off of 21st century warming. So it's not zero. So is the protocol working? I think it's fair to say that it is working. If we look at the amount of chlorofluorocarbon 11 in the atmosphere, we have stations all around the world, so we can divide it up into zones if we want to. You can see the northern hemisphere gets ahead of the southern hemisphere because more people live here and we've emitted more of it here. This is when the emissions began to turn around 1990 after the London meeting, as I told you. And this is what chlorofluorocarbon 11 is doing now. But if emissions were zero, the northern hemisphere and the southern hemisphere would merge. And they're not quite merging. That's been a conundrum, actually, for scientists. We expected them to merge by now, or get very close to it. And recently, last week, a paper was published in Nature announcing that there's good evidence, not only from this difference between the hemispheres, but also from direct measurements on the ground, that there's an additional small source coming out of Asia. We don't know which country. We don't know for what reason. It may just be an accidental byproduct of making something else, like a plastic. It might be that someone is still making a little bit, but it's not huge. As you can see, this is where we expect it to be by now, is line number 1, and this is where we actually are. So we've still dropped tremendously, and if you look at the other chlorofluorocarbons, this is only one of about a dozen molecules that are important. They've pretty much behaved almost as we expected. So in the last few minutes, I just want to talk a little bit about the influence on climate. Ozone loss is not a cause of global warming. Professor Manabe just gave you a beautiful explanation of how carbon dioxide drives climate change. It is the primary cause of climate change. So ozone loss is not what causes global warming. The ultraviolet light that ozone absorbs actually gives you skin cancer, but it doesn't heat the planet's surface. Visible light is what heats the planet's surface. But one thing that absorbing that ultraviolet light does is actually to heat the stratosphere quite significantly. It's the major source of heat to the stratosphere. So when we completely destroy the ozone, as we have in the Antarctic, the stratosphere gets much colder. And you're probably familiar with the concept of a polar vortex. You can have a cold, tight vortex, in which case Sweden stays relatively warm because all the cold air is bottled up over the Arctic. Or you can have a wavy vortex, in which case you can get quite cold with a push of Arctic air over you. And of course, it can also come down over us in North America, too, depending on how the waves look. The Antarctic vortex in the stratosphere has gotten much colder because there's no ozone in it now at certain times of the year. And what that, in turn, has done is to actually lead to a shift in where the jet stream sits, and it's made the winds stronger. So you can see how the winds here have strengthened. What that's actually done is to make it, so that's just the trend in the strength of the vortex, if you will. It's made the Antarctic plateau region colder than it would have been since about 1979 or so. And the peninsula region has gotten very hot. So the Antarctic Peninsula is one of the places with the strongest global warming of any place anywhere. Some of that is certainly carbon dioxide, as Professor Manabe talked about, but it's also due to the change in the structure of the vortex and the structure of this wind system. So the ozone hole has really rocked the climate of the southern hemisphere. That wind change, this position of the jet stream has also affected rainfall, extremes. It's had a big effect everywhere, but particularly the peninsula. You can see it's actually made South America a little warmer too. So there's more, in short, there's more warm maritime ocean air hitting this region and less of this cold polar air from the continent hitting that region. And it's also made it windier. That in turn has an effect on ice, and I just in the last minute want to say something about ice. The Antarctic has what are called ice shelves, and you can actually, they do kind of look like a shelf. This is the edge of the Larsen B ice shelf from a photograph taken in 2008. That's just a tongue of ice that's extending way out over the water. As those ice shelves melt, they do not contribute to sea level rise because they're already sitting on the ocean, but they do destabilize the ice behind them. And so you can imagine that as you lose that buttressing ice shelf, the flow of ice into the water can increase, and that's happening quite noticeably on the peninsula and in other parts of that part of Antarctica. And I would argue there's clearly a contribution to that from this change driven by ozone, which has, I think, contributed particularly, and I need to actually get my cursor in there, which is always difficult. I'm going to have to exit the show so I can do this. Come on. Yes, I took that picture. It was really fun. Here we go. So what you can see there is the breakup of an entire ice shelf. I hope it's clear, even though it's small. In a period of about a month, the Larsen B ice shelf just completely disintegrated. That happened in February and March of 2002, and it was certainly driven in part by the warming of that region that is happening because of the ozone loss. And that, in turn, will lead to more flow of ice into the ocean from all these surrounding glaciers. And actually, the loss of glaciers in the Antarctic is a significant cause of sea level rise. So I apologize I couldn't get that going without doing that. But let me just, in the last minute, say a few words that may help us to kind of think about at least my view of the contrast between the two issues. So if you look at ozone depletion, I've already emphasized my 3 Ps. It's perceptible because of these fingerprints that we have scientifically. They can be understood by I've even given simpler versions of this talk to high school students, and they get it. Personal health impacts always make people more concerned about environmental issues, and we know we have practical solutions. I mean, particularly for spray cans, people could make a change without the need for policies. But we also did have some great policy, and some fantastic diplomats helped to pave the way, as well as engineering and innovation to really find even more practical solutions. When we come to climate science, the puzzle is a lot more difficult. We do have a great physical understanding, as was described. We're seeing more and more fingerprints emerging, things like the Arctic warming faster than lower latitudes, for example. And they're becoming more and more perceptible in many places. Not everywhere, but in some parts of the world it's becoming pretty obvious that summers are getting hotter than they've ever been before, and certainly extreme heat is a serious problem. There's no universal personal health impact on everyone right now, and it's actually the poorest people of the world, the developing countries that don't have the capacity to adapt, that are the most vulnerable. So climate change challenges us to think beyond ourselves, actually, at least for us in the developed world. To consider issues of what's fair globally is absolutely essential, I think, if you're going to deal with climate change. That's a challenge for people, but it's one we have to rise to. Policies have been, I think, very thoughtful, and I don't think you can argue that the solutions aren't practical. They have become practical. So It's amazing how quickly electric vehicles have come on. It's incredible how fast renewable energy is becoming available and cheaper all the time. So really one of the big policy questions is to spur innovation and technology so that alternative energy becomes cheaper and faster and better all the time. So I remain optimistic on climate change. It is a very challenging problem also just because of the embeddedness of energy into the global economy. Very, very different kind of problem than the way the chlorofluorocarbons were. But the story of the Montreal Protocol demonstrates that global policies can be put in place, that people can agree and they can work. So it's just to summarize the things that I've said and to thank you very much for listening. Thank you.
Thank you very much, Susan, for a brilliant talk and the optimistic end. I think we need that. Questions to Susan? Yeah. Lars-Olof?
Wait for the mic. Here it comes.
Paper by Monskat or last week that you referred to, CFC 11, I think. Do you have any idea? I think it's not due to new production, it's something leaking somewhere, right?
We don't know. It's possible that it is coming out of old refrigerators. Some of it certainly, we can say, is coming from old refrigerators, old air conditioners. Here in Sweden and actually also in Japan, people do a great job of recycling the chlorofluorocarbon out of those systems when they get rid of them. But in other parts of the world, including actually my country, we don't do as well. So there's always leakage from what we call the banks, which is what Olaf, I believe, is referring to. And I think that's contributing. I'm actually trying to do an analysis of that within my group right now. I'm excited about doing that. But the evidence that other people have looked at suggests that there's a particular source somewhere in Asia. We don't know what country. So there could be some production. And as I said, it isn't necessarily chlorofluorocarbon 11 that they're trying to make. I think if it is happening, I don't think it's because someone's cheating on the protocol. I think my best guess is it could be an accidental emission because chlorofluorocarbons are used as feedstocks in making certain kinds of plastic. And it might be that the containment in those factories is just not good enough, and so they have a leakage that they aren't doing on purpose, but need to do more work to contain. That's a possibility, or someone could be cheating. That would shock me. China and India have closed down the plants that they had, and we know that the main plants that they had, they have been closed. There's no question. Those aren't operating. So it's either it's not something you can make in the garage. So I just don't think that it's likely to be deliberate. But I think it's going to be a fascinating thing to research. Yes?
Birgitta?
Birgitta has a question.
I've always been amazed by the process in these years, 85 to 87, sort of, and how fast everything happened. And I would like to hear your comments, if it really was that fast as we from outside see it, or if you have been thinking about stratospheric clouds before 85, and as a follow-up on that, do you think the Antarctic ozone hole saved us in a way to make the Montreal Protocol happen?
Yeah, that's a great question. Let me answer the last part first. I think if we hadn't had the Antarctic ozone hole, we probably wouldn't have phased everything out as quickly as we have. And that would have meant more chlorine building up every year, and more ozone depletion at mid-latitudes going on. Now, it is also true, though, that by 1988 or 89, We knew that there was already ozone loss at mid-latitudes in places like Europe and North America from ground-based measurements. It wasn't as dramatic as Antarctica. It wasn't 50%, but it was 5 to 10%. One of the best places to see that actually is the Swiss record from Arosa, which goes back 100 years almost. That's just an amazing record. And you can see stable, 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 and then, you know. So it's not huge, 5 to 10%, but it's measurable. So even at mid-latitudes, we were seeing bigger changes earlier than we expected. I think those would have driven action too, but they would have become much worse if it would have taken more time. I think the world was shocked into quick action by the discovery of the ozone hole, which saved us from having an even worse problem, absolutely. The other part of your question was how quickly the evidence came together. I did not personally think about polar stratospheric cloud chemistry until the ozone hole was discovered. But people have known for hundreds of years that polar stratospheric clouds exist. There's fantastic books about observations of them, mainly in Scandinavia, actually, going back centuries. And there were satellite measurements already. And people, even the early explorers, Robert Falcon Scott saw polar stratospheric clouds. If you read his diary, you can see sentences that he wrote about it where he clearly was seeing polar stratospheric clouds. So the link that I was fortunate enough to think about was, hey, you know, maybe hydrochloric acid and chlorine nitrate might react on those things. I had a little bit of a tip-off, I have to be fair. A few years earlier, some laboratory chemists had thought that they saw a reaction between those two molecules happening in the gas phase at a very slow rate. It would be a very unlikely reaction. It's a four-center reaction, which I'm not going to talk about, but you know, you can see, I think, the picture. So that caused a little bit of a stir in the scientific community at the time. If that reaction was going in the gas phase, it would have huge consequences. But quickly, they realized, oh, no, it's not actually happening. It's just an artifact because it's on the surface in our reaction vessel. We put the hydrochloric acid and the chlorine nitrate in a tube, and hey, we think we see something, but don't worry, it's only on the surface. Well, after the Antarctic ozone hole was discovered, I began thinking about this, and I said, oh, surfaces, well, what about clouds? Now, it's been a long time coming to have a complete understanding of the physics and chemistry of those clouds. Another thing that we got lucky with is we thought initially that they were water ice. They turn out to more often be made of liquids, sulfuric acid, water, and nitric acid, and also nitric acid trihydrate ices. So the composition of those clouds is more complicated than we thought. But it doesn't matter what they're made of for reasons that are a little complicated, except I can say when it gets cold enough, any kind of surface gets reactive. So a lot of that has to do with water depositing on the surface and giving you what's sometimes called a quasi-liquid layer in the physical chemistry community. And that allows processes on ice surfaces that are a little bit wetted to be very similar to a liquid. So we got perhaps lucky on that in a sense. Otherwise, we would have really had to work hard to understand the microphysics of those clouds, what they were made of, and that would have taken longer. But the other thing that we had great good fortune was to just have these kind of instruments. The instrument that I worked with at Visible Spectrograph had been developed about 10 years earlier, and the main reason was because of concern about supersonic transport. It was designed to measure nitrogen dioxide. So the fact that people were starting already to think about stratospheric chemistry and what chemicals could be measured is why all this instrumentation was all in place already. You know, we had all the instruments. Some of them had been flown on balloons, but we didn't know what was going on in Antarctica because we didn't have satellites then. So the only way to we had satellites just for ozone. We had no satellite measurements of any of the chemicals. Today we have satellite measurements of chlorine monoxide and hydrochloric acid. I mean, if it was happening now, we would know everything. But at the time, the only way to really find out was to go to Antarctica, measure it on the ground, just take the instruments down there, which is what we were fortunate enough to do. And I was very lucky to be a young scientist in exactly the right place at the right time. And I'm very lucky to be with you today. Maybe we should have a break.
Well, I have a short question to you. Do we know if the fauna of Antarctica were kind of impacted?
Yeah, there may be people here who know more about this than I, and I'd be welcoming any contributions on that. It's been discussed a lot whether phytoplankton could be sensitive to the enhanced ultraviolet. I think the evidence suggests that that may not be such a big problem because they can go deeper in the water column and escape the UV. One thing, though, that I am becoming very concerned about personally is krill. So krill are the base of the Antarctic food chain. They, feed the penguins, they feed the fish, which feeds the whales and the seals and everything else that lives in a very, very rich, biodiverse ocean. But the krill spend the winter on the bottom side of the sea ice. So they're larvae, and then they come up and they feed on the algae and stuff on the bottom side of the sea ice. And sea ice in that part of Antarctica that I showed you where the ice shelf has fallen apart is also disappearing. Other parts of Antarctica, the sea ice is actually growing, but that is exactly the region where the krill are the most abundant, is where that ice is going away, partly because of ozone, I would argue. So I'm going to be very intrigued to see how that plays out. We know that the krill population in that part of the Antarctic has decreased dramatically. We know that some kinds of penguins have seen decreases in population there. So it's a matter of some serious concern. I think, biology is quite complicated. It's much harder than chemistry. It's why I become a chemist instead of a biologist. So I think it'll take many years to sort that out. But whatever is causing that decline in Antarctic sea ice, if it's global warming or ozone depletion, and I actually believe it's a bit of both, the implications for the planet are enormous.
Yes.
We'll see.
But we are still optimistic.
Well, we have to change our ways, right? I mean, when we say things like Professor Manabe said, and I said myself yesterday, it was reminded to me that I sounded too pessimistic when I said, well, we think we're going to see 2 to 5 degrees Celsius of global warming in the coming century. Well, that's only if we don't change our ways. And of course, if we change our ways, we could keep it to 2. To get below 2, we probably have to get very creative with ways to sequester the carbon, but people are thinking about that too. So the practical needs to move along, and policies can spur innovation on that. People don't have a simple thing that they can do that gives you a big reduction in emission. There's lots of things that we all, I would argue, can do and should do to be wise users of this planet. It's great how many bicycles we have here in Sweden. That certainly helps to avoid unnecessary carbon emission, but it's not going to give you the kind of reductions that we need. We really need to change the energy system, and so the most important thing a citizen can do is be engaged and demand that the policy people actually do the kinds of things that will allow that to happen. If we could just throw away our hairspray, we would. This is a little different. Okay.
Thank you very much. You can take that at the panel discussion later on. Yeah. So we have 25, 30 minutes break for refreshments, and then we'll have a panel discussion afterwards. Thank you very much.